So this is a continuation of video part 7, logistic regression. In part 7 we observed that if 75% of Ni greater than equal to 10, then deviance and Pearsonian chi-square will be approximately chi-square. Otherwise, will not approximated by chi-square. So this is the restriction for deviance and Pearsonian chi-square statistic. So we need a new statistic when this situation arises. That means 75% of Ni does not meet this condition. G-square statistic. As before, another popular statistic is G-square, which is likelihood ratio statistic for whether the parameters except intercept term beta naught are 0, that is the significance of parameters in the model for G-square, the larger model always has bigger G-square, since it has more parameters. In the model. This is a sort of like sum of square due to regression. Again, to test for significance of parameters in M2 versus M1. This is defined in our videos part 7, logistic regression. We can use del G square M2 given M1. This is G square M2 minus G square M1. Which is the change in G square for model 2 versus model 1. Thus, the likelihood ratio statistic for two nested model can be calculated using either del G square or del D square. Suppose we want to test beta I equal to 0, then del G square is equal to log likelihood beta curl hat given HA minus log L tilde beta tilde given H naught is equal to sum over I from 1 to n, sum over I from 1 to n yi log pi I hat by pi I tilde plus 1 minus yi log 1 minus pi I hat by 1 minus pi I tilde. This is follow chi-square with 1 degrees of freedom, because under alternative number of parameters is k plus 1 and under H naught the number of parameters is k, so the degrees of freedom of chi-square is 1, where pi I hat estimate under HA and pi I tilde estimate under H naught. Now we consider Hosmer-Lemeshow goodness of fit statistic, where NIs are small. Suppose the responses are Bernoulli and are not naturally grouped into binomials, either because there is a continuous covariate or many covariates, so that the grouping would lead to sparse data. That is, suppose that more than 25% of Ni less than 10. So we already mentioned, in that case, deviance statistics or Pearsonian chi-square we cannot use because they are not approximated by chi-square. So again I repeat this thing. Suppose the responses are Bernoulli and are not naturally grouped into binomials, either because there is a continuous covariate or many covariates, so that the grouping would lead to sparse data. That is, suppose that more than 25% of Ni less than 10. Then assume yi follow Bernoulli with probability pi I. Then we want to determine if the model pi I equal to e to the power beta naught beta 1 curl prime xi curl by 1 plus e to the power beta naught beta 1 curl prime xi is good fit. One possible way is to fit a broader model with interactions and or squared, cubic, etc. terms and see if those extra terms are significant. Hosmer and Lemeshow suggest forming G usually ten extra term Hosmer-Lemeshow suggest forming G with usually 10 extra term or extra covariate or explanatory variables based on combination of the covariates xi curl in the logistic regression model. You again test if these extra covariates are significant. Now we consider an example. Suppose there are one covariates, say x, and we have small n number of observation. Then we fit the model pi I equal to e to the power beta naught plus beta 1 xi by 1 plus e to the power beta naught plus beta 1 xi I from 1 to small a. We could form 10 extra terms or groups based on decile of covariate xi. That is, we could form 10 extra term or groups based on this decile of covariate x, that is, we form 10 groups of approximately equal size. That means first group consists of n by 2, n by 10 subjects with smallest values of xi. The second group consists of n by 10 subjects with the next smallest values of xi, and so on. And the last group contains the n by 2 subjects with the highest values of xi. Suppose we define 9 indicators and the last one is redundant. Then capital I small ig equal to 1 if individual I is in group G 0 otherwise. Then we see that if we do this thing, then 75%, this thumb rule, 75% of Ni should be greater than equal to 10. So, to test the goodness of fit, we consider alternative model, that is our M2, logit pi I, beta naught, beta 1 xi, these are additional covariate parameters Q9 I 9. If model logit pi I beta naught beta 1 xi is appropriate, then gamma I should be 0 for all I from 1 to 9. So this is the null hypothesis. and each of these statistics would be approximated by chi-square with 9 degrees of freedom, because these are additional parameter, gamma 1 to gamma 9. Therefore, for general logistic model, pi I e to the power beta naught plus beta 1 prime xi curl beta 1 curl prime xi curl by 1 plus e to the power beta naught beta 1 curl prime xi curl, in which the covariates can be continuous and method of forming the extra covariate is not obvious. In this case, Hosmer-Lemeshow suggests that we form groups based on deciles risk. If pi I hat is equal to e to the power beta naught hat plus beta 1 curl hat prime xi curl by 1 plus e to the power beta naught hat plus beta 1 curl prime xi is a predicted probability of failure for the given model, then Hosmer-Lemeshow suggests forming groups based on deciles of pi I hat. That is, we form 10 groups of approximately equal size. The first group contains the n by 10 subjects with the smallest value of pi I hat. The second group contains the n by 10 subjects with the next smallest values of pi I hat. And the last group contains the n by 10 subjects with the highest values of pi I hat. And you can show that if there is just one covariate X, then we get equivalent groups whether we base the grouping on xi or pi I hat, because pi I hat is a monotone transformation of x. So we are looking at the fit of general model pi I e to the power beta naught plus beta 1 curl xi curl by 1 plus e to the power beta naught plus beta 1 curl prime xi curl, and we define capital G groups indicators as capital I small g 1 if individual I is not in group G, 0 otherwise, where groups are based on deciles of risk. Then, to test goodness of fit, we consider the alternative model logit pi I equal to beta naught plus beta 1 curl prime xi curl plus gamma 1 I small I1 gamma 9 capital I small I 9 I from 1 to small n. Effectively, we are forming an alternative model used to test the fit of given model. Even though capital I small ig is based on random quantities pi I hat, asymptotically we can treat the partition as based on true pi I, and thus we can treat capital I small ig as a fixed covariate. if model logit pi I equal to beta naught plus beta 1 curl prime xi curl is appropriate, then gamma I equal to 0 for all I from 1 to 9. Then to test the fit of the model, we could use a likelihood ratio statistic a score statistic or a world statistics for h naught equal to gamma I equal to 0 for I from 1 to g minus 1. Suppose we have G group, and in that case we use, if we use decile, then this capital G equal to 9. And in generally this is the null hypothesis. And each of these statistics would be approximately chi square with capital G minus 1 degrees of freedom if model fits, that means under H naught. The score statistics only requires the estimate of beta naught beta 1 under the null, but both the likelihood ratio and the world statistic require the estimate of gamma g from the alternative model. So note that the score statistic only require estimates estimate of beta naught beta 1 under H naught but both the likelihood ratio and world statistic require the estimates of gamma g from the alternative model. Hosmer-Lemeshow in 1982 suggest using Pearsonian chi-square based on the grouping of observation chi-square HL. I denote this statistics by chi-square HL, H for Hosmer, L for Lemeshow, equal to sum over G from 1 to capital G. Since we have capital G group equal to big O, that is the observed frequency of small gth group, minus Eg, this is the expected frequency of small g group, whole square, divided by small ng, that is the size of small gth group, divided by Eg by Ng into 1 minus Eg by Ng. After simplification, we get sum over G from 1 to capital G, big O small gk minus Egk whole square by Egk, where when y equal to 0, that is, we treat this failure as failure, then OG1 simply OG and EG1 is simply EG, and when y equal to 1, that is success, then this OG2 is equal to Ng minus capital OG and Eg2 equal to small ng minus capital G. Basically, this is Pearsonian chi-square applied to G cross table of observation. So this statistics is nothing but a Pearsonian chi-square applied to capital G cross 1 cross 2 capital G cross 2 table of observation and expected count in the G group. So please stay with us. We will continue this topic logistic regression in our next class. Till then, thank you.